Hi, in this video, we're going to talk about how we can predict the period of a simple harmonic motion system. Now, there are a couple words that we should know. Those include amplitude, period, and then frequency. And you can see on the video right now that I have defined those three things already for you. I didn't think it was going to be the best use of our time to watch me write these three definitions. However, I would like to speak a little bit about each definition as you copy it down. So let's start with amplitude. Amplitude is usually shortened to a capital A, and it is the magnitude of the displacement of the oscillating object away from its equilibrium position. So if we were to kind of visualize the amplitude of perhaps a mass spring system, we would first want to know, where is our equilibrium position? So I'll just draw this little dotted line to represent equilibrium. And we know that when an object is on a horizontal mass spring system, it oscillates around that equilibrium position. And the amplitude is how far we go to either the left or to the right of that equilibrium position. And we go the same amplitude both to the left and to the right. Okay, so we're going to oscillate equally around that equilibrium. And the same thing happens when we look at a pendulum as well. So I'm going to draw a real quick pendulum here. Oh, I would like that line to be a little bit straighter. There we go. So here's a pendulum. It swings to both sides. Again, we should define where our equilibrium is. So I'll just use that little red dotted line to represent our equilibrium. And we know that our amplitude is going to be how far we swing from that equilibrium point right there in the middle, either to the left or to the right. And just like a mass spring system, we would expect to see that the amplitude both to the left and to the right of equilibrium is the same for a pendulum. Now, since amplitude is a length, we use meters to measure it. Let's go on to period. So period is the time interval needed to complete one full cycle. Since it is a time, we like to use T as our shorthand, but since we are talking about a very specific time, we are going to use a capital T in order to do that. And when I say one full cycle, that's really important. We should really key in on that. Let's take our pendulum, for example. The period of the pendulum is the time it takes not only for that pendulum to swing out, but also for that pendulum to swing back to its original position, right? That's what we are talking about when we talk about one full cycle. And since this is ultimately just a time, we are going to use seconds as our default unit. Frequency is another way to kind of talk about how often things are occurring in something like simple harmonic motion. It is talking about the number of cycles completed in 1 second. So I'd like to quickly compare frequency and period to each other, because if you notice, right, period is a time to do one full cycle. Frequency is cycles in 1 second. So these things are actually inverses of each other. We kind of gather that just from their definitions. The fact that period is the inverse of frequency, and by extension, frequency is the inverse of period. So that's an important thing for us to keep in the back of our mind. It's not necessarily information given to us on the equation sheet, but it is a part of the definition of these two words. Now, frequency, the unit of frequency, it's named after a guy. It's named, I believe, hertz. And hertz is really just another way of saying inverse of seconds. Since the frequency is, or since the period is equal to 1 over frequency, and since period is seconds, that must mean that frequency has a unit of 1 over seconds. All right, so now that we got that vocabulary out of the way, let's actually get to kind of the meat of this lecture, where we want to talk about period for our various simple harmonic motion systems. So let's start with the pendulum. Now, were we in the lab, we would try to create an experiment that would allow us to evaluate how various variables may affect the period of the pendulum. So let's brainstorm some of those pretty quickly here. What are some things that may affect the period of the pendulum? Usually, when asked this question, new physicists will say, well, perhaps changing up the length of our pendulum will change up the period. Perhaps changing up the mass of the pendulum bob. Pendulum bob is the mass that's hanging out at the end of the string, the thing that actually swings back and forth. Perhaps changing that up is going to change up our period. Perhaps changing up our amplitude, which could also be measured by looking at the angle of release. Oh, I misspelled release for this pendulum, right? The angle of release, how far we pull this back, right, is directly related to the amplitude. So it's two different ways to kind of measure the same thing. And were we in the lab and we actually performed these 3 experiments, what we would find is that yes, when we change up the length, in fact, we do change up the period of our pendulum. And the relationship that we would get from our data would look something like this. We would have period on our y, we would have length on our x, and we would end up getting this kind of sideways opening parabola, right? So we would get this y squared relationship. I'm going to come back to this relationship here in just a second. But I would like to also talk about the experiment where we change up the mass of the pendulum bob and see how that affects the period. And we would actually find that those things are unrelated to each other. Changing up the amplitude and how does that affect the period? We would find that those 2 things are unrelated as well. So the only thing that actually affects how long our swing is, right, the time for one full cycle, the only thing that matters out of this list is the length of the pendulum. And so it's from this data that we can come up with an equation that will allow us to calculate the period of a pendulum, just knowing some basic things like length. So from this data, right, we know that this is a y squared relationship. So we would get something like t squared is equal to some kind of slope times length. And since this is a 0, 0 y-intercept, I'm gonna leave off the plus b. And if we did a whole bunch more investigations, we would actually find that the number for this slope, it's gonna look like a crazy number, but it would be 4 pi squared over g. So the equation for this data that we see right here is period squared is equal to 4 pi squared over g times the length of the pendulum, where g represents the gravitational field of wherever the experiment takes place. And we more commonly like to write this not as t squared equals 4 pi squared over g times L, but instead we like to take the square root of everything and write it as period is equal to 2 pi times the square root of L over G. And the reason why we prefer to write it this way is because ultimately we are looking for an expression that is going to calculate for us the period of the pendulum. And this directly calculates the period of the pendulum for us. And this equation is provided to you on the equation sheet. So I always advocate that you should memorize equations, but don't feel pressured to, because it is going to be available to you. And what we're going to do is we're going to use this equation in a practice problem here. So a pendulum suspended from a ceiling almost touches the floor at its equilibrium position. If it has a period of 12 seconds, how high is the ceiling? So we want to know, what is this length of our pendulum? We are going to assume that this experiment is happening on Earth. I don't know how many Martians have homes with ceilings, so we'll assume that this is on Earth. And so let's use this equation that tells us how period and length of the pendulum are related to each other. We'll substitute in 12 seconds as our period. We'll substitute in 9.8 meters per second squared as our G. And so the only thing that we don't know is L. And from here, right, it is purely algebra in order to solve for that length. So we'll divide 2 pi out from the right-hand side of the equation, and we end up with 1.91 is equal to the square root of L over G. So let's square both sides of the equation to get rid of that radical that's on the right-hand side. And we get 3.65 is equal to L over G, which is 9.8. Maybe I should put 9.8 in all these locations. Woo. Here, I'll replace this with 9.8. 9.8. Because then, right, in order to get L by itself, we say, oh, I got to multiply both sides by 9.8. We end up getting 35.7 meters as the length of our pendulum. Thus, 35.7 meters is the height of our ceiling, which is pretty huge. We're talking like over 100 feet tall. I think we're hanging out in some kind of amphitheater maybe with ceilings that tall. All right, now when we think about simple harmonic motion, we're not just thinking about pendulums, we're thinking about mass spring systems as well. So let's touch on what affects the period of a mass spring system. Okay, so let's brainstorm variables that may affect period, but this time we're referring to a mass spring system. Again, if we could do all this in the lab, that would be fantastic. We may brainstorm that perhaps the amplitude, so the amount that we pull our mass away from equilibrium in order to set it into simple harmonic motion, perhaps that is going to change, or I should say, by changing that, we change our period. We may also suspect that changing up the spring constant will change up our period. We also may just guess that changing up the mass at the end is going to change up our period. And these are the variables that we would pretty classically come up with. So again, if we wanted to in class, we could come up with, we could perform these 3 different experiments, and we would find that amplitude does not seem to affect the period at all. So much like in a pendulum, amplitude and period have nothing to do with one another. But we would find that yes, our spring constant is going to affect our period, and we would find that yes, the mass that we have oscillating at the end of the spring will affect our period. Okay, so there are 2 things here that we have control over that can change up the period of a mass spring system. And I'm just going to jump to the relationship rather than going through the derivation from the data. I'm going to jump to the relationship here. Period of a mass spring system is equal to 2 pi times the square root of the mass divided by the spring constant. And notice that there are a lot of similarities here between this relationship for mass spring system and the relationship for a pendulum, right? We, in both cases, have a factor of 2 pi involved. And in both cases, we are actually taking the square root of our set of variables. Now, what variables we are using changes depending on whether or not we're thinking about a pendulum or we're thinking about a mass spring system. But it's interesting to note that the structure of these two equations is largely the same, which really does tell us that simple harmonic motion has a lot more things in common than not. So let's finish this lecture by doing an example problem where we are dealing with the period of a mass spring system. So we have a spring with a cart at its end, and it vibrates with a frequency of 6 hertz. So in our mind's eye, we can conclude that this must be some kind of horizontal mass spring system, because here's this cart, right? And we have a spring that's causing it to vibrate, right? It's oscillating. So we want to know, what is the period of vibration? Well, the information that we have is the frequency, and we know that period is equal to the inverse of that frequency. So let's do 1 over 6 hertz, and we get that this period is 0.167 seconds. Oh, very good. Part B says determine the period if the cart's mass is doubled. We're going to double the mass of this cart while the spring constant remains unchanged. Okay, we don't really have a lot of new information given here. We are kind of working underneath some old information, right? If I write out the relationship for period of a mass spring system, originally, right, in part A with just the one piece of mass on the cart, we really only have the fact that this period is equal to 1.167 seconds. Don't know what that mass actually is, don't know what that spring constant is. And now they are telling us that they're going to double your mass. Okay, so again, the relationship for a period of a mass spring system, right? The only info that we have is the fact that now this is supposed to be 2m, but we don't actually know what m is. We don't actually know what k is. But notice how this and this are not that different from each other. In fact, it appears that the only real difference on the right-hand sides of these equations is this 2 underneath our radical. So what I'm going to do is I'm actually going to take this 2 underneath the radical. I'm going to pull it out front so that I now have root 2 times 2 pi times the square root of m over k. And from part A, we know that 2 pi times the square root of m over k is the same thing as 0.167. So why don't I take that root 2 and just multiply it by 0.167 and find that when I add mass to this mass spring system, I end up getting a period that has increased to 0.236 seconds, which makes sense, right? I'm adding more mass. It should be harder to make this thing oscillate. It should take more time for it to oscillate. And that's exactly what we're seeing right here is the time of this bigger mass to oscillate is larger than our original mass to oscillate. All right. Good luck solving problems.